Welcome to another edition of VirtualX MasterClass with Mr. Kanyile. Today I want us to look at the Euclidean geometry. This is the geometry that was discovered by a guy called Euclid, hence Euclidean geometry. We want us to go straight to past papers and see how do we solve these problems. But there's one thing that I want to show you. How do you master this session called the Euclidean geometry? There are only 13 theorems that you need to master because all the questions revolves around these theorems. But another important factor is, of course, your grade 8, grade 9. It comes out in your matric examination. Hence, my session for today will start back there. We'll look at how grade 8, grade 9 assist us in our grade 12 matric exams, move to grade 10 to 11, where we'll be talking about cyclic geometry, as well as grade 12, the 3 theorems that we need to understand at grade 12. This guy Euclid said this geometry originated from just a point. This is a point. This is where Euclidean geometry originated from. All the geometry that you study, it comes from just a point. This guy Euclid noticed something when you put a group of points together. When you put a group of points together like this one, he ended up having something like a line segment. There's so much Euclid that we can learn from just a line segment. We've got 3 types of line. The first one is called the line segment. This one is called a ray. This one is called a straight line. Remember, all this originated just from a point. And if you put 2 lines together at a common point, this is a line, this is another line. And this point here is called a vertex. Something is formed. What is formed there? An angle. This is called an angle. And we've got different types of angles. In fact, we've got 6 types of angles, we've got 6 types of triangles, and we've got 6 types of quadrilaterals, the 4-sided figures. We'll all be going over that section. It is important that we must understand our angles because it will make our Euclid much more easier, and it can even assist us in analytical geometry as well as trigonometry. If you go to your Cartesian plane, it can cover all the angles that we have. Let's look at it. If you've got your Cartesian plane, remember, this would be 0 degrees, this will be 90 degrees, this will be 180 degrees, this will be 270 degrees, and back to 360. Now, all the angles are catered in this Cartesian plane. The angles that are found in the first quadrant, this is the first quadrant, second, third, and fourth. The angles found in the first quadrant, in other words, angles that are above 0 degrees but less than 90 degrees, an angle here, we'll call them acute angle. We said we've got 6, so the first one is acute angle. An acute angle is above 0 degrees but less than 90. What about the angle which is exactly equals to 90 degrees? Perpendicular. This is 90 degrees. This is called a right angle. That's the second type of an angle. The first one is acute, the second one is right angle. The third one is in the second quadrant. From there to here, it's above 90 degrees but less than 180 degrees. It's called obtuse angle. So all angles that are found in the second quadrant are called obtuse angle. After that, we go to a straight line. From here to here, we form a straight line. So this angle is exactly equal to 180 degrees, and we refer to it as a straight line. From there, from here, we go beyond the straight line. An angle that is here is called reflex. Even if it's here, it's also called reflex. So a reflex occupies 2 quadrants. Both the third and the fourth quadrant is the reflex angle. And the last one is called revolution. Angle which is exactly equals to 360 degrees is called revolutions. So these are the 6 types of angles. In your grade 8, that's what you learn, and it will come up in your grade 12. For example, when you talk about angles, if I've got an angle like this, I've got x here, I've got 2x here. In your grade 8, you'll find a question like this and say, solve for x. The question is not actually asking you to find x. It is checking you whether you understand the types of angles. What do we call an angle from this side to this side? It is called a straight line, and it is exactly equal to 180 degrees. From here to here, it's 180 degrees. So I know that all angles that are in this one, they add up to 180 degrees. So solving for x, they was just checking you whether you understand the types of angles rather than solving for x. We know that this angle plus that angle is 180. That's what you must know. X plus 2x will give us 180 degrees. Reason, we've got a straight line. Reason is the very important factor in your Euclidean geometry, because for every statement there must be a reason. So how many x's? This is 1x, these are 2. Together they are 3. So 3x is equals to 180 degrees. Then if I'm looking for x, I divide by 3 on both sides. Divide by 3 this side as well. Divide there once. So x is equals to 3 into 1 does not go. 3 into 18, 3, 6, 9, 12, 15, 18 goes 6 times. 3 into 0 does not go. So x will be 60 degrees. So this is 60. This is 2 times 60 with 120. 60 plus 120 will give us the total of 180 degrees. That's how you go about solving this. And you'll see this in a complicated diagram in your Euclidean geometry. Maybe you'll have a figure like this one. You'll have something like this one. You've got this. You should not lose if I've got 60 here degrees. I must be able to find y. Even in a complicated diagram, I must be able to pick this one up and see that if I'm adding this plus that, it is 180 degrees. Then my y will be 120. I should not lose the sight of this even in a complicated diagram, because this is how we ask you these questions. That was the types of angles that I wanted to talk about. From there, let's quickly go to triangles quickly, because we're rushing into grade 11 Euclid. So these were angles. If I've got this one, I can see an angle. If I close here, how many angles do I see? I've got another angle there, I've got another angle here. How many angles do we have? We've got 3 angles. Do you know that those tricycles that have got 3 wheels? We call them tricycles because tri means 3. So this is 1, 2, 3, 3 angles. So it's tri for 3 and angle. So that's how this was named. It's triangle. It means there are 3 angles in that figure. Just like in the angles, we start in types of angles, we've got 6 types of angles. So as well as in triangles, we've got 6 types of triangles. It is one of the richest part of our Euclid. It goes from grade 8 up to grade 12. It becomes a theorem in grade 12, things that deals with triangles. What's important there is the first theorem that you learn in triangles, that the sum of interior angles of a triangle are supplementary. This angle plus this angle plus this angle is equal to 360 degrees. Even if you see it in a complicated diagram, don't lose that. If you add those 3 angles, it will give us 180 degrees. If we add them, they give us a supplementary. Supplementary angles means add up to 180 degrees. Complementary means add up to 90 degrees. I said we've got 6 types of triangles. Let's quickly look at them. Number 1, we've got let's look at this one. If this side is the same as this side, the same as this side. Equal sides, equilateral. Lateral means sides, so equal sides. This triangle is called equilateral triangle. This is equilateral triangle, simply equal sides. Now, if the sides are equal, then the angles will also be equal. This is 60, this is 60 degrees, this is 60 degrees. These properties are very important. Angles have got 2 properties. Triangles have got 2 properties. One has to do with angles and one has to do with sides. These sides are the same, equilateral sides. Therefore, all the angles will also be equal. Number 2, I've got to talk about the Scalene triangle. I'll try and move as quickly as I can. I'm not going to put it in a standard position. This angle has got that side opposite it. This side has got that angle opposite it. So if the angles opposite equal sides will also be equal. If these sides are equal, those angles will be equal. If these sides are equal, those angles will be equal. If these sides are equal, those angles will be equal. You can use your fingers to make life easier. So angles opposite equal sides are equal. That's another theorem that you apply in your grade 12 maths. So we know that this is called an isosceles triangle. So that's the second one. The third one, is called scalene triangle. Scalene triangle. What do I know about a scalene triangle? In a scalene triangle, this side is not equals to this one, it's also not equals to that one. So in this particular type of a triangle called the scalene, there are no equal sides, hence no equal angles. No angle is equal to, and nothing is equal in that one. So those are the first three. So what about the next three? The next three types of triangles are named according to one of their angles. Now, triangle number 4, look at this angle. What type of an angle is that one? Remember, from the types of angles, the angle that is exactly equals to 90 degrees, it is called a right angle. But if we close it, we have a right-angled triangle. This triangle is named according to one of their angles. In this particular case, a right angle. So this is a right-angled triangle. This is a very important type of triangle, because this is the triangle that gives us the theorem of Pythagoras. Remember, you will use it a lot in your Euclid as well as in your analytical geometry. What is it saying? This side is called the hypotenuse. The longest side is called this side is called the hypotenuse. It is the side opposite 90 degrees. It's called the hypotenuse. Out of the three sides that forms this triangle, this will be the longest side. Now the theorem says, in a right angle triangle, the square on the hypotenuse is equal to the sum of the squares on the other two sides. It means that this side squared plus this side squared will be equals to that side squared. That's the theorem of Pythagoras. Pythagoras is the name of a person who discovered this theorem. He said, in a right angle triangle, the square on the hypotenuse is equal to the sum of the squares on the other two sides. Others will even say x squared, which is this side, x squared plus this side, which is y-axis, y squared is equals to r squared. This will be your theorem of Pythagoras. That's what it literally means. But you must understand it that the square on the hypotenuse is equal to the sum of the two other sides. Right, that's a right angle triangle. This is the triangle that also pushes you to trigonometry, because trigonometry is divided into three parts. There's the first part that deals with a right angle triangle. There's another part which deals with angles with triangles which is not a right angle triangle, and the last part will deals with 2D, 3D. Now here it's a right angle triangle. It takes you to the first part of trigonometry, where you talk of your definition. So sine, so katoa. Sine is opposite of hypotenuse. That's where the hypotenuse comes in. When you define those theorems, they are coming from a right angle triangle. So katoa, right? That's the right angle triangle. Number 5. Remember, I said this angle, these three are named according to one of their angles. What type of an angle is this one? What type of an angle is this one? It's an acute angle. If I close this, I will therefore have acute angled triangle. One of its angles must be an acute angle. Then we'll have an acute angle triangle. Number 6, let's look at this triangle. Remember, this is 0, this is 90, this is above 90 now, but less than 180. So it's in the second quadrant. So this angle is obtuse. So if I close it, I will have an obtuse angled triangle. Right, these are the 6 types of triangles. There are so many theorems that we need to understand when we talk of triangles. I said the first one was that if I've got a triangle like this one, if this is A, B, C, so I know that angle A plus angle B plus angle C will always be equal to 180 degrees. This is very important. This is another very important theorem that we must know. It will assist us a lot. Number 2, another theorem that has to do with triangles. Look here. If I have a triangle like this one, and I've got an exterior angle, this comes up a number of times in your exams. Even at the end of this year, you will have a theorem that will require you to understand this theorem. This one says this angle is called the exterior angle. This is the triangle. The inside here we've got interior angles. This one is the exterior angle. We must not lose the sight of what we are learning here, that from here to here is 180. If I've got this one, I will know this one. Because if I add these two, I will get what? 180 degrees. But this theorem that I want to talk about here, it's called the exterior angle of a triangle. It says the exterior angle of a triangle is equal to the sum of the two opposite interior angles. In other words, the theorem says this angle will always be equal to this angle plus this angle. So if I add these two angles, I will get this one exactly as it is. So you might be given this angle and this angle, you are required to find this one. You should not be confused. You must know that this one is equal to that plus this one, and you'll have only one unknown. So the exterior angle of a triangle is equal to the sum of the two opposite interior angles. That becomes important. I repeat, the exterior angle, this one outside, is equal to this one plus this one. I should not be confused. No matter where the exterior angle is, let's extend it this side. Can you see where is the exterior angle? This becomes the exterior. Therefore, this angle will be equal to this plus this. The exterior angle is equal to the sum of the two opposite interior angles. So that one, even if I extend it from this side, so this one will be equal to this plus that. So that's called the exterior angle. Now, there are so many other theorems that has to do with triangles. I've just spoken about the exterior angle. Let's talk about the concept of congruency. It comes in triangles as well. We're still on triangles. There's another concept called congruency. What do you mean by congruent? If I've got this triangle and another triangle exactly the same as it, congruency, it's like the identical twins. If you've got the identical twins, they are born on the same day, they are born by the same parents, everything about them is the same, and they look the same, they walk the same. That's what we mean by congruency. I'm just addressing the concept congruency. Congruent means equal in all respect. Now, we're saying these two triangles are equal in all respect. In other words, if I take this triangle and put it on top of this one, it will be like there is only one triangle because they are the same. What does it mean? It means that this angle is equal to that one. This side is the same as this side. This one will be the same as this side, and this side will be the same as this side. Hence, this angle will exactly be the same as this one, when this one will be exactly the same as that one. So if I take this and put it in here, it will be as if it's one triangle. So that's what congruency means, equal in all respect. Now, when you cut someone in between, the piece this side will be exactly the same as the piece on the other side. If there is a shoulder here, there must be a shoulder on the corresponding position. Remember corresponding position. If there's a shoulder here, there must be a shoulder on the corresponding position for it to be congruent. If in one case there's a shoulder here and the other shoulder is here, it's no longer congruent because it should be at the corresponding position. Like if this angle must be equal to this one, you can't have this angle equal to this one. It should occupy the same position, corresponding position. So that becomes important when it comes to congruency. There are 4 cases of congruency. You don't have to check everything before you conclude that the two triangles or the two things are congruent. In this case, when we talk of congruency, we refer to them to triangles, even though there are so many other objects that are congruent, but in mathematics, because we want to make life easier, when we talk of congruency, we refer to triangles. There are 4 cases of congruency. I'll quickly go over them. 1, it's side, side, side. What do you mean by side, side, side? We mean if I've got 2 triangles, I've got to show that this side is the same as this side. That's the first side. So side compares to 2 sides of 2 triangles. So when we say side, we are saying this side is equal to this side. When we say side again, we're saying this side is equal to that side. The last S, this side is equal to that side. If that is the case, if we've got 2 triangles with 3 pairs of corresponding sides, this side corresponded to this one, it takes the same position. This one corresponded to that one, and this one correspond, we call them corresponding sides. Remember, we talk of corresponding and there are no parallel lines. Don't only confuse corresponding with parallel lines only. It has to do with position rather than parallel lines. Now, when we say side, 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 we are comparing these sides that they are the same. If the sides are the same, if one side is equal to this one, and this one is equal to this one, and this one equal to this one. Therefore, the corresponding angles will also be equal. You don't have to prove the corresponding angles. Automatically, they will be the same. That's the first one. Number two, it's side, angle, side. What do you mean by side, angle, side? Let me just make an example. If this side is the same as this side, that's side. If this angle is the same as this angle, that's angle. And this side, the same as this side. I can't take that other side because the angle is here. Because the angle that we must, that is involved is called the included side, the included angle. What do you mean by the included angle? We mean the angle that is between the two sides that we're talking about. Remember, we're talking about this side and this side. I can't go take another angle. I've got to take the angle that is in between the sides that I'm talking about. That's what we mean by included angle. The angle that is between the two of these sides. All right, that's side, angle, side. The third one will be angle, angle, side. The fourth one will be 90 degrees, hypotenuse, and the side. Of course, this one will work in a right angle triangle because there's 90 degrees and there's hypotenuse. So if we're comparing two triangles that are congruent and it's a right angle triangle, we go to this case of congruency. The fourth one, which is 90 degrees, hypotenuse, and side. That's another important feature in your Euclidean geometry. If we understand congruence, it will be easier for us even to prove theorems when we go to grade 11 and 12 stuff. Another concept after congruence that I want us to understand is the concept of similar. This is still grade 9. Similarity. This also comes out in grade 12, and yet it's the concept that we have learned in grade 9. Similar does not mean equal, but they look the same. For example, you and your mother, you look the same, but you are not equal. You are not of the same age. Maybe you walk the same way, maybe you talk the same way, maybe so we say you are similar. You are not congruent. Congruent, it's like identical twins, equal in all respect. Similar, one is big, one is small, but they look the same. They even talk the same, they walk the same. That's the concept of similarity. And it is there at the end of this year where they say that prove that these two triangles are similar. Right, similarity. Let's make an example. We've got, this is your mother or your dad, and this is you. You look exactly the same. The only difference is that your dad is big or your mother is bigger than you while you are still young. If this is A, B, C, this will be D, E, F. You've got those two triangles which are similar. Similar simply means there are features that are the same between you and your parent. In this particular case, the angles, because we're talking about triangles here, those features will be angles. Those angles must be the same, the corresponding angles. The eyes, your eyes and the eyes of your parents, they are in the same position. You can't have eyes here and eyes here. The eyes must be in the same position for it to be similar. So in this particular case, if this one is equal to that one, this one, this angle here, angle B, is equal to angle C, angle E, and angle C equals to angle F. Then we can say the two triangles are similar because they've got the same features. The corresponding angles are the same, equiangular. That's the concept that we use when we say two triangles are similar. We say they are equiangular. It means that their corresponding angles are the same. This one corresponds to that one, it's the same thing. This one corresponds to this one. If we've got such a situation, we say the two triangles are similar. We compare the three corresponding angles that they are the same. And when you prove it, you don't have to prove all three. Because when I add this plus this plus this, what do we get? 180. When I add that plus this, what do I get? 180. So if I can show that this is equal to that, that's one angle. Number two, if this is equal to that, that's the second angle. Obvious, this one will be equal to this one because it would have been the third pair. Because both of them, when you add them, they give us 180. So if this one is equal to that, and this one is equal to that, you can conclude by saying that angle C will be equal to angle F, because it would have been the third pair, because both of them, they add up to 180 degrees. So when you prove that the two triangles are similar, focus on two angles. Check the two angles that you can equate between the two triangles, then you can conclude on the third one and say it is the third pair. So that becomes crucial when proving this. Now, similarity only does not deal with angles, and there's got some special features that has to do with sides. This theorem says, if two triangles are similar, what we mean by similar, we mean corresponding angles are the same, where A equal to D, B equals to E, and C equals to F. That's what we mean by similar. Now, if we have that situation, then the ratio of their corresponding sides will be the same. What do you mean by that? If I've got two triangles that are similar, it simply means that this side, which is AB, over ratio of something over the corresponding side there. This is AB, it corresponds with which side? This side, with DE over DE will be the same as AC corresponds with which side? That side, DF. We can even add the third side, BC over EF. This will, if this is the case, therefore the two triangles are also similar. If the ratio of the corresponding sides are the same, then the two triangles are similar. The theorem says it's a metric theorem that you need to prove. The proof of the theorem is required in grade 12. It says if two triangles are similar, then the ratio of their corresponding sides will be the same. Ratio is the same of the corresponding side. This one corresponds with that one, so this over this is the same as this over that, or the same as this over this. In a practical situation, you might let's do it like this. Let me take this one off and compare these two. In a practical situation, you'll be given 3 dimensions and you're required to find the 4th one. You'll be given 3 and you're required to find the 4th one. Let's make an example. If these two triangles are similar, and we are told that we don't know the value of this side, let's call it x. Let's call this one 5 units. Let's call this one 8 units. This one corresponds with that one. Let's call this one 4 units. Okay. What do you do when you've got a scenario like this one and you are told that these two triangles are similar? Or at times you need to prove that these two triangles are similar by showing that this is equal to that and this is equal to that, then conclude that this one is equal to that. Then you can say the two triangles are similar. How do you go about solving for x if the two triangles are similar? Remember that if two triangles are similar, then the ratio of their corresponding sides are the same. In other words, this ratio must be the same as this ratio, must be the same as this ratio. Let's write down. Let's solve for x. How do we go about solving for x in a problem like this one? We know that since the two triangles are similar, then x, which is AB is x over BE, over DE, I mean. What do we see in DE? We see 5 is equals to AC. What do we see in AC? We see 8 over DF. What do we see in DF? We see 4. Then you solve for x. You cross multiply. So x will be equals to 8 over 4 times cross multiply times 5. What is 8 over 4? 4 into 8 goes 2 times. What is 2 times 5? It is 10. So x is 10 units. If you are not given the dimension, this is 10 units. You can see that one is half of the other one. If this is 8, what is the corresponding side? It is 4. So if this one is 5, what will be that side there? It will be 10. Hence we got 10 there. This is how you go about solving this theorem. Remember that we are just talking about triangles. We started from a point, we develop into lines. So these are the triangles. What else is important? I think when we're talking about lines, I think there's another very important part which we left out, which I want us to go back to. If we've got these lines, let's look at these lines. Let me call this 1, 2, 3, 4, 5, 6, 7, 8. Right. Do we have corresponding angles there? What does corresponding has to do? It has to do with the position. This one is on top of the line and number 5 is on top of the line. So those are corresponding angles. Some people would think that things will only correspond when they are parallel lines. There are no parallel lines here, yet we say angle A corresponds with angle D. So corresponding has nothing to do with parallel lines. But let's involve parallel lines and see what I'm trying to show you here. Once we have this line and this line, and I'm saying these two lines are parallel and they're cut by a transversal line, if I've got 1, 2, 3, 4, 5, 6, 7, 8. In this case, this side, in the first diagram, angle 1 corresponds with angle 5. Angle 1 corresponds with angle 5. We call those corresponding angles. When we talk of corresponding angles, like angle 1 corresponds with angle 5. This side, also angle 1 corresponds with angle 5. What is the difference between these two corresponding sides? These two corresponding sides are not equal, because the lines are not parallel. Where the lines are parallel, then the corresponding angles are equal. So when you see parallel lines, you think of this. Where we talk about corresponding angles, in this particular case, the corresponding angles will be equal. In this particular case, corresponding angles are not equal. Angle 1 is equal to angle 5, reason corresponding angles. Angle 2 is equal to angle 6, reason corresponding angles. So it has to do with position. You see this position, it is the same position as this one. And you can see this is an acute angle, small, that's an obtuse, the same. Acute, the same. So this one corresponds with this one, they are equal. 4 is equals to 8, 2 is equal to 6, 3 is equal to 7. Those are called corresponding angles. They occupy the same position. We also have alternate angles here. 3 is alternate to angle 6. They are equal if the lines are parallel. 3 alternate to 6, but they are not equal because these lines are not parallel. So 3 is equal to 6 alternate angles. 4 equals to 5 alternate angles. These are called interior alternate angles. They are inside the parallel lines. We also have those that are outside. This one is alternate to 7. Angle 2 and 7 are exterior alternate angles. Angle 1 and angle 8 are also alternate angles. This will assist you even in a complicated diagram. We'll look at this where there are parallel lines. In your exam, you only talk about twice with parallel lines. It's when you talk about this scenario where we will look for alternate angles, corresponding angles, or when you look for the theorem called the proportionality theorem. When say a line drawn parallel to one side of a triangle divides the other two sides proportionally. We'll do that one later. Also here, which is important, are called co-interior angles. Co-interior angles, they must be on this line is called the transversal line. These two lines are co-interior angles. They are on the same side of the transversal line. In the same way, 4 and 6 are co-interior angles. All the time when you add the co-interior angles, you'll get 180. In other words, angle 3 plus angle 5 is equal to 180. So if I've got this one, angle 3, as equals to 60 degrees, I will know that angle 5 will be 120, because 60 plus 120 will give me 180. So if I've got one, I must be able to find the other one. So this one plus this one are co-interior angles. Interior means inside parallel lines. We also have co-exterior. Angle 1 and angle 7, they add up to 180. They are co-exterior angles. So is angle 2 and angle 8. They are also co-exterior angles. This becomes important. It always comes out in your examinations. In fact, in all the papers, you will see this either in analytical geometry or in Euclidean geometry. So it comes in handy. Then the next part will be your quadrilaterals. Your quadrilaterals will help you more when you are dealing with of course, your analytical geometry, because your analytical geometry will deal with figures. The four-sided figures, there are also 6. It is important that we must also master them. From here, I want us to go straight to grade 11 Euclidean geometry. I want us to look at one theorem that is done in grade 10, which is called the Midpoint Theorem. If we've got a triangle like this one, what is the midpoint theorem saying? If I've got a line halfway, if this is halfway, in other words, if this distance is the same as this distance, and I've got a line that is drawn parallel to this line, and also this part is the midpoint. So this is the midpoint, that's the midpoint. The theorem says, if this is the midpoint, this distance from here to here will be half of this distance. In other words, If this is drawn in the midpoint, and this one is 2 centimeters, the theorem says this definitely will be 4 centimeters. This is what the midpoint theorem says. If you don't understand this theorem, it will make your working a bit difficult. So it is important that you learn this theorem from grade 10. It's called the midpoint theorem. If this is drawn from the midpoints, this distance of this line will be half of this distance. So that's a very important theorem from your grade 10. Now let's move over to grade 11 geometry, which is called the cycle geometry. Remember, there are about 13 theorems that you must master as a matriculant if you want to go to the exams. There are about 10 theorems there from grade 11. The bulk of Euclid comes from grade 11. And there are only 3 theorems that you need to study in grade 12. So if you master your grade 11, half the battle is won. Let's look at the 10 theorems that you need to understand at grade 11. Right, Mr. Kanyile wants more VirtualX MasterClass. I want us to look at how do you master the grade 11 Euclidean Geometry. It's all about theorems. All the questions that we ask you in the examination revolve around these 10 theorems. The way that you put, let's understand them first. Let's look at this theorem. Let's come back to the grade 11 Euclidean Geometry. You say what you see. This is the center of a circle. Remember, this is 90 degrees. That's why we did angles. There's a line that is drawn from the center of a circle. How is it drawn? This line is called a chord. This line is drawn perpendicular to a chord. It forms 90 degrees there. The theorem says whenever you've got this scenario where there's a line drawn from the center of a circle which is drawn perpendicular to a chord, it will divide that chord into 2 equal halves. What is this saying to us? It means that whenever I've got a line drawn from the center of a circle perpendicular to a chord, I don't have to be told that this side here is the same as this side. Remember what I've written in red, it was not there. It is implied by the fact that there's a line that is drawn perpendicular to a chord. It bisects the chord. Bisect means cut into 2 equal halves. It's an examinable question which says, complete the following. A line drawn from the center of a circle perpendicular to a chord, then says complete that one. You will say a line drawn from the center of a circle perpendicular to a chord bisects the chord. It means cut the chord into 2 equal halves. In the examination, you might be required to prove that. To prove that this side is the same as this side. How would you go about doing that? We are going to employ congruency, the concept you will learn in grade 8, grade 9, where you will have the 2 triangles. You join these 2, you compare the congruence between these 2 triangles, then you will be able to show that this one is equal to this one. We'll do the proofs together later on. That's the one theorem. A line drawn from the center of a circle perpendicular to a chord bisects the chord. Let's go to its converse. This one is coming from the center of a circle. It's coming here to bisect this chord. What does this imply? It implies that the angle there must be 90 degrees. This theorem says a line drawn from the center of a circle to the midpoint of a chord, halfway, midpoint of a chord, is perpendicular to a chord. Let's say that again. A line drawn from the center of a circle to the midpoint of a chord is perpendicular to the chord. What is the mistakes that we usually do as learners? We will say a line drawn from the center of a circle to the midpoint of a chord bisect the chord, which you'll be repeating the same thing. Midpoint means bisect. So the theorem, you say what is not here. What is not here is that 90 degrees. So you bring it back. You've got this here, but you don't have 90 degrees. So that's what you'll be proving. You prove what is not there. A line drawn from the center of a circle to the midpoint of a chord is perpendicular to a chord. So you prove that this angle here is 90 degrees. Of course, the same way, using congruency. Let's come to the third one. So in other words, these 2 theorems, when we prove them, we'll have to use congruence. That's why I've put them together. Let's look at these 3 theorems here. All these 3 theorems have got something to do with the center of a circle. These 3 theorems here have got something to do with the tangent. So all this has to do with the tangent I put together. And these 2 here, they are cyclic quadrilaterals. There's a quad inside the circle. We call them cyclic quadrilaterals. Let's come to these 3 that deals with the center. This is the center. This is the center. Here I don't see a center. But then why do we include this in these 3 that has to do with the center? We'll come back to that. This is called an arc. This is an arc. This arc forms an angle at the center. It subtends, we call it subtends the angle at the center. The same arc subtends the angle at the circumference. Now these angles, they are subtended by, it might be a chord. It might be a chord here. A chord subtends the angle at the center. The same chord or arc subtends the angle at the circumference. What is the theorem saying when you've got this scenario? It's saying an angle subtended by an arc or chord at the center is twice the angle subtended by the same arc or chord at the circumference. It means that this angle here is 2 times bigger than that angle. If that one here on top is x, what will this one be? It will be 2x. So the one at the center is 2 times bigger than the one at the circumference. It should not be anywhere else. One must be at the center and one must be at the circumference. It does not only have to take this position. It can be something like this. Let's look at it. This is the center. This is the circumference. So this one is 2 times bigger than this one because it subtends it at the center. It also subtends it at the circumference. There are about 12 other ways where you can interpret the center theorem. We'll show you in the next slide. So this one is called the center theorem. The angle subtended by an arc or a chord at the center is twice the angle subtended by the same arc or chord at the circumference. If the one at the center is 100, what is the one at the center there? It will be 50 because the one at the center is 2 times bigger than the one at the circumference. Let's move on to another theorem. All this has something to do with a center. Now this is also a center. What do we call a line that passes through the center to the other side of the circumference? It's called the diameter. Now remember when we were doing the types of angles, what do we call this angle from here to here? It's called the straight line. And it is how many degrees? It is 180 degrees. That's why we started there. This angle here is 180 degrees. Now watch here. This one goes to the center and this one goes to the circumference. This one is 2 times bigger than that one. Look at this one. This is my arc in this case. It goes to the center. This arc, I repeat, this arc goes to the center. The same arc goes to the circumference. So this one is half of that one. This one is 2 times bigger than that one in actual fact. So if this one is 180, what will that one be? It should be 90 degrees. So the angle subtended by the diameter will always be equal to 90 degrees. This one is taken from that one. The fact that the angle at the center is 2 times bigger than the angle at the circumference. When we talk about this one, we said angle subtended by the diameter or angles in the semicircle. We simply know that this is the angle subtended by half circle, which will be equal to 90 degrees. So this was not there. We must be able to know the theorem. Number 5. This is called an arc or a chord. If we have an arc, or we might even have a chord here, this arc or this arc forms that angle at the circumference. Remember this one, the one was at the center, the one was at the circumference. Now the same arc forms the angle at the circumference, the same arc forms another angle in the circumference. Now both these angles are the circumference. You can't have one being half of the other one. Because this arc forms the angle at the circumference, the same arc forms the angle at the circumference. These two angles are subtended or are formed by the same arc or chord at the same position, at the circumference. Then we say this angle will be equal to this one. Angles subtended by an arc or a chord at the circumference are equal. This theorem is important when you do your riders. The angles subtended by an arc or chord at the circumference are equal. This is what we look for in a complicated diagram when we do our examinations. Even if I'm coming from that side, this one will be equals to this one. This one will be the same as this one, subtended by that chord. If I'm coming from this side, this chord forms that one, the same chord forms that one, subtended by the same arc or chord. It might not be on the same position. Let's make an example. If we have something like this chord is equal to this chord, but this chord forms that angle, and this chord forms this angle. If this chord is the same as this chord, they will form equal angles. Remember, this chord forms this angle, and this chord also form these angles. These two angles will be equal because they are formed, they are subtended by equal chords. They don't necessarily have to be in the same position like this one. They can be in different position. As long as they form the angle in the circumference, those angles will be the same. So this is very important. Why then do I include this in problems that has to do with cycle? Because when I want to prove that this is equal to this, I will have to create a center somewhere. Let's create a center and see what I'm trying to tell you. Dotted lines, construction. So this angle is at the center. This angle here is at the center. It goes to the center, it goes to the circumference. So this one is 2 times bigger than that one. This one is at the center, this one is at the circumference. So this one is 2 times bigger than this one. Let's repeat. This one is 2 times bigger than this one, center theorem, which is that theorem. This one center, this one circumference. So this one is bigger than, 2 times bigger than that one. I repeat, this is 2 times bigger than this one. This one is 2 times bigger than that one. Therefore, this one will be equal to this one. But both of these are 2 times bigger than this one. So that's why we put this one in a center, because when we prove them, we've got to include a center. I repeat, the center theorem, the angle at the center is 2 times bigger than the angle at the circumference. This one, angle subtended by the diameter is equal to 90 degrees. Here we say angles in the same segment are equal. This chord divides the cycle into 2 segments, the bigger segment and the minor segment. And both these angles must be at the same segment. So we say angles in the same segment are the same, or angles subtended by the same arc or chord. Let's move on to those theorems that has to do with the tangent. If I read a statement in my question paper and say this line is a tangent, I don't have to think about all other theorems. I've got to think of these 3 theorems, because these are the only theorems that deals with a tangent. If I'm reading a statement in the exams and say this line is a tangent, then I've got to start to look for this, because this is what is being tested. Do I see this in the diagram? If I see it, I apply it. Do I see this? Do I see that? Depends what will be given at that particular time. This line is called a tangent. Of course, this is a chord. So if we've got an angle here, where is this angle? This angle is between a tangent and a chord. This angle will be equal to the angle subtended by that chord, formed by that chord at the circumference. If you take this chord, we form an angle at the circumference, it will give us an angle equals to this one. So we call this an angle between a tangent and a chord is equal to the angle subtended by that chord in the alternate segment. I repeat, the angle between a tangent and a chord is equal to the angle subtended by that chord in the alternate segment. That's how you call the theorem. You don't have to be stereotyped, you must be able to see it when it comes from the other side. When it comes from this side, this one, Nancy, chord it will be equals to this one. Must be able to see it from this side and from that side. We call this theorem tan-chord theorem. Remember, you must be able, okay, I'll come back to that one. Let's look at this one. What is the name of this line? It is the tangent. And what is the name of this line? It is the radius. All the time, whenever a radius meets a tangent, you'll always have 90 degrees. So it simply means that here, there's a 90 degrees that you are not told about. That angle there is 90 degrees. This is what you apply when you do your radius. It doesn't matter where it comes from. I can have something like this one. What is the name of this line? It's a tangent. If I can have a line from the center of a circle to there, which is a radius, I don't have to be told that this angle here is 90 degrees. It doesn't matter, it can come from any position. I can have a tangent there. If I've got a line there, 90 degrees will be formed. A tangent, a radius, at times we might confuse you and not use a radius and just use a diameter. It's the same thing, because this line and this line will form 90 degrees. Whether it's a radius or a diameter, it doesn't make sense. So this theorem is called tan-radius theorem. A radius is always perpendicular to a tangent. That's important. This line is a tangent, and this line is a tangent. What do I notice here? I notice 2 tangents that are coming from the same point outside the circle. This theorem says all the time the 2 tangents will always be equal. If up to the point of contact with the circle, that line to here, it will always be the same as this one to here, if they are coming from the same point outside the circle. The two tangents are equal if they are drawn from the same point outside the circle. So you look for this. If you see that there are two tangents that are coming from the same point, make them equal. That's what is being tested. The last two, it deals with the cyclic quadrilateral. Let's make an example. Let's say this is A, this is B, this is C, this is D. What does this theorem say? For this to be concyclic, it should touch the circumference for it to be a cyclic quad. Four-sided figure inside the circle. What does this theorem say? It says angle B plus angle D is equal to 180 degrees. This is what this theorem is saying. The sum of opposite angles of a cyclic quad are supplementary. Supplementary means equals to 180. In the very same way, angle A plus angle C is also equals to 180 because the sum of the two opposite angles of a cyclic quad are supplementary. Remember these things. This one is important because you need to prove this in the exam. There are 6 theorems here that you need to prove in grade 11 and 2 in grade 12. So that's the one that you must know the proof of it. This is another one that you must know the proof of it. 2, 3, 4. Let me call this one because it's the converse. There are 4 here in grade 11, and the 2 will be in grade 12 theorems. So in grade 11, this proof you must know either this one or this one. Number 2 is this one. Number 3 is tan chord theorem. Number 2 is cyclic quad, opposite angles of a cyclic quad. You must know their proof. It is examinable. That's bookwork. Now you must know that angle B plus angle D is equal to 180. Let's quickly do the proof of this theorem. What is important when you do the proof is that you must have the construction, and where the construction will come from the angles that you are not proving. Remember, we're proving that this plus this is equal to 180. Therefore, the construction will come from the other two. If I'm proving this, the construction will come from this. Now, to prove the theorem, I've got to understand this one. Our theorems, they get on top of each other, and they pull you towards the solution. What is this one saying? The center theorem. The angle at the center is twice as the angle at the circumference. So if I'm going to use this one in proving this one only works when there is a center. I've got to create a center here. That's where the construction comes in. I will create this as a center. Just call this my center O. That's one. Create a center O. Number 2, join AO, because the construction will come from those that I'm not proving. If I was proving this plus this, the construction was going to come from B and D. Because we're proving B plus D is equal to 180, I will have my construction like this one. What I'm trying to do there, I'm trying to create this scenario where I will have an angle at the center and the one at the circumference. I can see the angle at the center, the angle at the circumference. Let's call this center O. Let's call this O1. Let's call this O2. All right, that's what we have. This is our construction. Once you've done your construction, then you can prove. We want to prove that this is 180. Let's quickly do it. All right, we want to show that angle B plus angle D is equal to 180 degrees. It's a formal proof, it's required in your examination. Now, once you've got your construction, let's do it. Do I see this theorem here? Yes, I can see that angle O1, do you see this angle here? Angle O1, this one. It is subtended by this arc. It goes to the center, the same one goes to the circumference. So we can say angle O1 plus, angle O1 is equals to twice angle B, 2B, right? The angle at the center is 2 times the angle at the circumference. So O1 is equals to twice that one. Reason, center theorem. Right? That's what we got so far. In the very same way, we can say if I'm coming from this side, this is O2, it will be twice this one. So we can say angle O2 is equals to 2 angle D. Same thing, center theorem. right? Angle O1 is twice that one, angle O2 is twice this one. All right, that's what we have. But we've learned the types of angles. We know that, look here, this angle O1, this one, plus that angle. What do we get there? Revolution, 360. We know that angle O1 plus angle O2 will be equal to 360 degrees. That's our grade 8 revolution. Let me remove this quickly. Right. Remember, we want to prove B plus D is equal to 180. When I look at this, I don't have any B's and any D's, but I've got half of 180, which is pushing me towards that one. Can I bring, instead of O1 and have B's and D's, O1 and O2? Yes, I can do that, because I'm told that O1 is the same as 2 angle B. So where there's O1, I can introduce B where there's O1, instead of O1 and put 2B. There is O1. So instead of O1, I can push in 2B because these two are the same. So instead of O1, I can say 2 angle B plus, instead of O2, I want it in terms of B and D. In terms of O2, I can write what? 2D is equals to 360. I've done substitution here. I've substituted O1 with 2B. Okay, what is it that I'm looking for? I'm looking for angle B plus angle D, not 2B. I can see a common factor here. What is a common factor here? It is 2. Then I divide everything by 2. If I divide this by 2, I'll be left with angle B. Plus, if I divide this by 2, I will be left with angle D. If I divide this by 2, I'll be left with 180 degrees. This is proved exactly what I wanted to prove. So it is true that this one plus this one will give me 180 degrees, and I've proved it. It's a proof. It's about 4 marks in the examination. So you must be able to prove 1, 2, 3, and 4. These are the 4 theorems that you need to prove in your grade 12. And of course, the last one here is the exterior angle of a cyclic quad. If I've got a cyclic quad like this one, this theorem is saying the exterior angle of a cyclic quad is equal to the interior opposite angle. The exterior angle of a cyclic quad is equal to the interior. If I extend it this side, I can see the exterior. This will be my exterior angle. It is equal to that one as well. So you can prove all these theorems, but fortunately for us, we only need to show 4, which is 1, sum of opposite angles of a cyclic quad are supplementary. 2, the angle between a tangent and a chord is equal to the angle in the alternate segment, tan-chord theorem. 3, the angle subtended by an arc or a chord at the center is twice the angle subtended by the same arc or chord at the circumference. And the last one, the line drawn from the center of a circle perpendicular to a chord bisects the chord. This is one theorem because it is the converse. This one saying a line drawn from the center of a circle to the midpoint of a chord is perpendicular to a chord. This is the memorandum that you need to understand when you do Euclidean geometry, because all questions, they revolve around this. I want us to look at one more part before we go to exam questions. I want us to go and look at the slides that are prepared for you. It will make your life easier. Let's remember one thing. Euclid, the grade 11 part, is about the 10 theorems. The 2 that has to do with congruency, when you prove that. The 3 that has to do with center. The 3 that has to do with tangent. And the 2 that has to do with cyclic quadrilaterals. And I know where to look for solutions when I read the statement. Let's first remind ourselves about the parts of a circle. What do we call a distance around the circle? It's called the circumference. That line is called the diameter. Look at that line there. What do we call it? It's the radius. Look at that line there. It's not going through the center. It's called a chord. What does the chord do? It divides the circle into 2 parts, the major segment and the minor segment. There is a major arc and the minor arc as well there. The one on top, this one is called the bigger arc. And this one below is called the minor arc. minor arc, the smaller arc, minor arc. What do you call that piece of pizza that is formed by the radii? This piece is called a sector. A sector, minor sector, small piece, and a bigger piece, and a bigger sector there. Look at that line here. What is the name of that line that touches the figure at one point? That line is called a tangent. This one is also called a tangent. Let's put it in there. That one is also called the tangent. All these lines are called tangents, as long as they touch the figure at one point. These are the theorem, converse theorem, chord bisector. A line drawn perpendicular to a chord and passing through the center of a circle bisects the chord. We've got a line that is drawn perpendicular to a chord. What does it do? It bisects the chord. It makes this side equals to this side. Right, it bisects the chord. That theorem is important. An example, if you go to the exam and we're going to find the length of OS, where is OS? This is OS. How do you go about doing this? Applying this theorem. Because we've got the same scenario. We've got a line that is drawn from the center of a circle perpendicular to this chord. What does it do? It bisects the chord. So this side from S to the center is the same as from here to the other side. If this whole distance is 8 centimeters, if I don't know this theorem, I will never see that the distance from here to here is 4 centimeters, because this line bisects this chord. So if it is 8, so this line from there to here is 4 centimeters, and this one from there to there, it is 3 centimeters. I'm looking for that one. Now, what type of a triangle is this one? It is a right angle triangle. How do we go about finding OS? You use your grade 8, grade 9 theorem, Pythagoras theorem, that OS squared is equal to this side squared plus that side squared. If this is 3 squared, this is 4 squared, which is 16. This will give us 25. So that side, S squared will be 25. SO squared will be 25. Therefore, SO will be 5. So that becomes important using the Pythagoras theorem, that OS will be equal to 5. The terminology is important. That simply means subtends. We've got arc AB subtends angle X where? At the center. That's how you read it. Arc AB subtends angle X at the center. Arc AB subtends angle Y at the circumference. I'm introducing the center theorem now. Whether the arc or the chord, it does the same thing. Chord AB subtends angle X at the center. They can be subtended by the arc or a chord. The same chord subtends angle X at the angle Y at the circumference. This theorem, the center theorem, this one is 2 times bigger than that one. It doesn't matter where it comes from. It can come from any position. This arc forms this angle. If the same arc can form another angle at the circumference, that one will be half of this one. That one is at the circumference. So this one is half of this one. If I want to equate these two, Y and X, I've got to multiply this by 2. Arc or a chord does the same thing. It doesn't matter. I can take it from this side. Right? This is AB, subtends at the center. Let's take this, it's the same AB to the circumference. Let's look at it. We are taking AB to the circumference. Therefore, this one is 2 times bigger than this one. Center theorem. Arc or a chord does the same thing. Let's look at more problems. This is the 8 different ways in which the center theorem can come out. We know this standard position. The angle at the center is twice the angle of circumference. So this arc forms this angle at the center. The same arc forms it at the circumference. I hope you see this one. Arc goes to the center. The same arc goes to the circumference. Let's look at the third one. This is my arc. This is my arc, it goes to the center. The same arc goes to the circumference. So this one is 2 times bigger than this one. Let's go to this one. This is my arc, it goes to the center. The same arc goes to the circumference. So this one is twice that one. You don't always expect it to come this way. It can come in 8 different ways. Let's look at this one. This is the arc, goes to the center. The same arc goes to the circumference. Remember, this is 180. If this is 180, therefore that one will be 90. Let's look at this one. This is the arc. This is the arc. This arc goes to the center. So this angle here. The same arc goes to the circumference. It's that angle here. So this angle and this angle. So this angle is 2 times bigger than that one. So you must be able to see it no matter how it comes in these 8 different ways. These are all center theorem. So what is this saying to us? If the angle at the circumference is x, what will be this one is? What will this one be? If this one is x, what is that one is? It will be 2x. So the one at the center, this one, is 2 times bigger than this one. So that's important. I must be able to see the center theorem no matter how it comes out. The angle subtended at the center of a circle by an arc or a chord is twice the angle subtended at the circumference by the same arc or chord. We say angle at the center or center theorem when you abbreviate it. I want us to take a few problems on this. Find angle x there. What is it that I notice? I notice the theorem. Nothing is being asked here by the theorem. This is the angle at the center, that is the angle at the circumference. Which one will be big? The one at the circumference or the one at the center? Yes, the one at the center. If this is 84, what is x? It will be half of that, which will be 42. Angle x will be equal to 42, reason angle at the center. Let's look at y here. This one is at the circumference, this one is at the center. Which one is big? This one is 2 times bigger than the one that we see. If this is 35, what is y? It will be 2 times 35, in this case, which will be 70 degrees. That's how you go about applying these theorems. That says the angle at the center is twice the angle at the circumference. Let's look at these ones as well. The angle at the center is twice the angle at the circumference. That's what I know. If you focus at what you know, you'll never go wrong. What is this question? The first one is asking for angle x. Where is angle x? X is here. How do I find x? I try and look up, I don't see the value, then I'm stuck. But I know that this distance from here to here is the same as the distance from there to here. What do we call that? Radius. Now, this makes this the type of a triangle which is called isosceles triangle. So if this is x, because these two are the same, OA is equals to OB, radi. Therefore, this angle here, 42, will be the same as this one. Because angles opposite equal sides are equal. So if this is 42, this angle hidden here will be 42. And I know that the sum of interior angles of a triangle are supplementary. If I know that this one is 42, this one is 42, I can't be able to find x, because this is x plus 42 plus 42 gives me 180, and eventually I will find x to be 96. I've used the isosceles triangle and the sum of interior angles of a triangle. The fact that OB is the same as OA, it makes this triangle OAB an isosceles triangle. If this is 42, then this one will be 42, then 42 plus x will give me 180 degrees. Then I say 180 minus 2 times 42, which will give me 96 degrees. So the value of x is 96, and x is at the center. I can find the value of y, because this one is 2 times bigger than that one. So to find the value of y, I take this angle, which is x in this particular case, I divide it by 2 to find the value of y. In that case, I will find my y to be 48 degrees, because I've used the center theorem, angle at the center. This one is twice than that one. If this is 96, therefore that one will be half of 96, which is 48 in this particular case. Let's look at the next one. But before that, let me share with you my theorem. There's a theorem that I discovered. The theorem says the angle between a radius and a chord is equals to the angle between a radius, this radius, and a chord is equals the angle between a radius and a chord plus the angle subtended by that chord are complementary. What am I saying? I'm saying this angle that is here, that is between a radius and a chord. It can be this one, a radius and a chord, either of the two, because this is 42, this is 42 as well. So whenever we've got an angle between a radius and a chord, plus the angle subtended by that chord at the circumference, you will always have 90 degrees. But don't apply this theorem yet, it's not approved. This angle plus that angle is equal to 90 degrees. Look here, if this is 42, what should we add to get 90? We should add 48. So it is exactly the same thing. So this angle plus this angle must be equal to 90. I see the same thing even here. So this angle plus this angle must be equal to 90. So it will make it easier to find that angle. So don't apply the theorem yet until it is approved. Right, let's look at angle P. This is angle P. All that I want you to do when you have a problem, look at the theorem. I can see the center theorem here, so the angle at the center, this angle P, is twice the angle at the circumference. If I've got that one, all that I need to do is to multiply this by 2 to be able to find P. So P is in actual fact 62 times 2. Mistake that we do, we'll say P is 31. So P is 124, center theorem, or angle at the center. If I've got P, I know that Q and this one are the same. So I've got Q plus 124 to get 180. And I've got only one known, which is Q. I can find Q to be equals to 28 degrees. If you use my theorem, 62 plus 28 will give you 90. So this is 28. That's how you can find 28. Right. I want us to move to another theorem quickly. The angle in a semicircle is a right angle. As I say the angle in a semicircle is a right angle, I should know that it's the angle subtended by the diameter. Let's make an example. This is the diameter, half circle, semicircle. Semicircle, semicircle, semicircle means half of the circle. So it passes through the center, which is the diameter. Forms an angle. The angle subtended by the diameter is equal to 90 degrees. So even if it does not look like 90 degrees, as long as it is formed by this diameter, it will be 90 degrees. Look at this one. This diameter also forms that angle. Let's form it here. This diameter also forms that angle. So no matter how it looks like, this angle here must be 90 degrees, that angle there is also 90 degrees, and this angle here is also 90 degrees, as long as it is formed by the diameter. If I'm given this problem, find the unknown angles below, stating reasons. So reasoning is important. This line goes through the center, it is the diameter. So I think of this theorem. Now watch, this one subtends angle A, and I'm required to find angle A. So what is angle A here? It is 90 degrees because it is subtended by the diameter or angles at the semicircle. Look at B. B is here. This is a diameter. It forms this angle. So all the time diameter would subtend an angle which is equal to 90 degrees. Hence the value of B will be 90 degrees angle in a semicircle. Let's look at C. This is what C is. What is this called? It's called a triangle. What is the sum of interior angles of a triangle? Remember, we've already found B to be 90. Angle B is 90. So we've got 90 here, we've got 70 here, we're short of that. Once we've got 190, we are short of another 190 to give us 180. So this is 70, so definitely that has to be 20. So 20 plus 70, it's 90, plus this 90 will be 180. The sum of interior angles of a triangle are 180. If we've got 70, we've got 90, we are short of 20 to have 180. So the value of C here will be 20 degrees. It has to be 20 degrees. The sum of interior angles of a triangle. Let's look at D. This is where D is. I look where it comes from. It is formed from that triangle here. And this line is the diameter. The angle is in the semicircle or subtended by the diameter. It forms an angle of 90 degrees. So D will be 90 degrees. Let's look at E now. Let's look at this angle E. I know that this is a triangle, this is a triangle, this is a triangle, this is a triangle, this is a triangle. So 90 plus 30 plus this angle gives me 180. We already have 90, another 90 will come from 30 plus 60. So this E must be equal to 60 degrees. So that's how you go about applying these theorems. Let's move on to another theorem. Angles subtended by an arc or a chord in the same segment are equal. Angles subtended by an arc or a chord in the same segment are equal. Let's quickly look at it. This arc subtends that angle there. The same arc subtends another angle there. Let's create the third one from the same arc. It doesn't matter, it doesn't have to be only two. I can have another one there. So all these angles, this one, and this one, they are all formed by this arc. We can all refer to them as the same. If this is x, that will be x, and this will be x. So they are subtended by the same arc, therefore they will be equal. It can be the arc or the chord. It does the same thing. Doesn't matter it comes from which position. This arc forms this angle. The same arc forms another angle here. Therefore, this angle will be equal to that one. If this is x, this will also be x as well. I can also come from this position. I can also come from this position and form that one. And this position form also this one. It can be y's. So those two will be the same if I'm coming from this position. It can be the arc or the chord. The chord that forms these two angles, which are the same. Angles subtended by an arc or a chord in the same segment are equal. So this one equals to this one because they come from this arc, or if I'm coming from this side, this one will be equal to this one. These two will be the same. Look at this angle, it's 38. It comes from this chord or arc. This chord forms that angle. The same chord also forms that angle. So this one is also 38. And this one will also be 38 because it is subtended by the same arc or chord. Yeah. This is the arc. This arc forms that angle. The same arc forms this angle. So these two are the same. In the very same way, if I'm coming from this side, that one is y. So this one will be 40, therefore y is 40 as well. Angles subtended by an arc or a chord in the same segment are equal. Let's go to the cyclic quadrilateral theorems. There are only two. The angles, the sum of opposite angles of a cyclic quadrilateral are supplementary, or they add up to 180. The sum of opposite angles of a cyclic quadrilateral are supplementary. Let's create it. That's a cyclic quad. These are the two angles that I'm talking about. The theorem says if I add these two, I will get 180. So y plus w is equal to 180. It cannot only be these. Even if we have angles here, these two angles, when I add them, I will also be able to get 180. So angle x plus angle z is equal to 180. This is what we check in a complicated diagram. If we do have opposite angles of a cyclic quad, we add them, it should give us 180. If I've got this one, I'll be able to find the other one. It doesn't matter how it looks like. Even if it might look smaller than this, as long as all four corners of a quadrilateral touches the circumference, it will be concyclic. It might look half of it. This is still a cyclic quad. 1, 2, 3, 4. It touches all four corners. 1, 2, 3, 4. So this plus that will be equals 180 degrees, or these two also equals to 180 degrees. And you must be able to prove this theorem. If I'm proving that this plus this is 180, the construction will come from these two. Let's look at, for example, of the same theorem. Let's look at it. Angle x. This is where angle x. What do we have here? We've got a cyclic quad. This is a cyclic quad. Cyclic quad, cyclic quad, cyclic quad. All right, let's work it out. I know that this angle plus this angle give me what? 180. Reason? Opposite sum of opposite angles of a cyclic quad. So if this is 85, the value of x there will be 95, because 85 plus 95 will be equal to 180 degrees. The mistake that we do as young learners, if I see 85 here, I will assume that is also 85. They are not equal. When I add them, I must get 180 degrees. So it's 85 plus 95, that will give me 180 degrees. Let's look at y. This is a cyclic quadrilateral. So this angle here, y plus 110, will give me 180. If this is 110, I need to add y to give me 180. What is this y? What is 110 plus what will give me 180? This should be equals to 70 degrees, because 70 plus 110 will give me 180. So the value of y should be equals to 70 degrees. So 110 goes with 70, 85 goes with 95. When we add, I get 180 degrees. Let's look at P. This is where P is. Remember, I said to you, you must be able to see the stuff, the basics that we've done earlier on, even in a complicated diagram. What do we call these angles in a straight line? When I add these two, what do I get? 180 degrees. So 135 plus P must give me 180 degrees. So if I'm looking for P, I will say 180 minus 135 to get P, which is equals to 45 degrees. So I've already found P by using my grade 8, grade 9. I don't lose sight of my basics. The sum of angles in a straight line, they are supplementary. So P plus 180, P plus 135 is equal to 180, hence P will be equal to 45. I've used a straight line. Let's look at Q. Is this a cyclic quad? Yes, it is a cyclic quad. What do I know about the sum of opposite angles of a cyclic quad? They are equals to 180. If I've got 70 plus what will give me 180? Let's go back here. Y plus what will give me 110? Y plus 70 will give me 110. So Y goes with 70 goes with 110. Now I'm giving you 70 here. What should be the value of Q? It should be 110, because if I add Q and 70, I will have to have 180. So the value of Q, angle Q, therefore, must be equals to 110. Opposite angles of a cyclic quad. Let's look at R. Let's read the theorem. An exterior angle of a cyclic quad is equals to an interior opposite angle. This is exterior angle. It will be equals to the interior opposite angle. In this case is R. The exterior angle is equal to the interior opposite angle, which is R in this particular case. So R will also be equals to 135 degrees. The exterior angle of a cyclic quadrilaterals. Let's look at other theorems. The tangent is perpendicular to the radius at the point of contact. Tan radius theorem. So if we've got a radius, and let's draw a tangent here, and a tangent, I should all know that this is 90 degrees or this is 90 degrees. I don't have to be told that this is 90 degrees. It doesn't matter where it comes from. I can have a tangent there. I must be able to see that that angle is 90 degrees. Even if I can have another tangent to this side and draw a radius from there to there, 90 degrees will be formed there. I don't have to be told that this angle there is 90 degrees. So the angle between a tangent and a radius is 90 degrees. Tan radius theorem. The angle between a tangent and a radius is always 90 degrees. Right. What is important is that when we do these problems, don't be lazy to read the statement, because the statement will take you towards the solution. Now, if OT is a radius and AB is a tangent, that's important. If OT is a radius, OT, this is a radius, and this is a tangent. Whenever a radius meets a tangent, 90 degrees is formed. So there's something hidden here for us that will make us to say mathematics is difficult. But the solution is here in the problem. We are told that OT is a radius and the other one is a tangent. Do we have a theorem that deals with the radius and the tangent? Yes. Whenever a radius meets a tangent, 90 degrees is formed. So the question is not actually asking for x. It's checking whether I know the theorem. X is thrown there to put you away from the actual question. The question is asking whether we understand that this is 90 degrees. Because after that we'll go to grade 8, grade 9. This angle plus that angle plus this 90, which is not there, which you must be able to imagine. This 90 will give me the solution of x. Because x plus 90 plus this one will give me the solution to find x. Because when I add these three, I'll get 180. So x will be then 54. 54 plus 36 plus 90 will give me 180. The sum of interior angles of a triangle. I've used the fact that I've got a tan radius and the sum of angles in a triangle. This is a radius and a tangent. This 90 was very important because I wouldn't find the x if I did not see the theorem first. So x there is trying to throw you off from the actual question that is being being asked. All that is being questioned in Euclidean geometry are the theorems. So I'm checked whether I understand that this is 90 degrees, then it will make my life easier. What angle is this? This is y. Don't look at y, look at the theorem that you might find there. What is the name of this line? This line is the diameter, and it subtends the angle y. This diameter subtends the angle at the circumference. Therefore, angle y will be 90 degrees, angle in the semicircle. Then the last one will be z. We've got 30, we've got 90, we've got z. They must give me 360. 360 is made out of two 90s. This is the first 90. Let's find the second 90 between these two. If this is 30, therefore this should be 60 to give me the second 90 to give me 180 altogether. So z must be equal to 60 degrees. So that's how you go about solving problems. Look at the next one, two tangents theorem. As I say two tangent theorem, you must be able to see the diagram. If two tangents are drawn from the same point outside the circle, then they are equal in length. Let's do the scenario. If this is P, let's draw a tangent from P to the diagram. That is the tangent. Let's draw another tangent. That is the tangent. If two tangents are drawn from the same point outside the circle, then they are equal in length. Now, don't misinterpret this theorem and say it says PR is equals to PU. Those are lies. These tangents are equal up to the contact with the circle, not beyond. Up to the contact with the circle. So PQ will be equals to PT, or PT is equals to PQ, not PR. They are equal up to the point of contact with the circle. So PT is equal to PQ. PT is equals to PQ, not PU equals to PR. That's lies. They are equal up to the point of contact with the circle. Let's have another scenario so that we understand what we're doing. Let's look at this one. PT is equals to PQ. There are two tangents drawn from the same point outside the circle. Those are the same. PQ and PT are the same. Let's make a few examples. Now we are not afraid of these types of problems. We are armed with our theorems. And we know that we will be reading this and will be directing us to where we find solution. From any point outside the circle, only two tangents can be drawn and they are equal in length. This is the tangent, this is the tangent. Let's read it. PQ and PT are tangents. Stop there. It takes me to the three theorems that deals with the tangent. The first one is tan-chord theorem. The second one is tan-radius theorem. Remember, there are only three theorems that deals with the tangent. Tan-chord theorem, tan-radius theorem, and two tangents from the same point. Once we say P, Q, and PT are tangents, I think of those three theorems only. And I check if I do have those theorems in the diagram. Let me start from the bottom. Maybe let's look at two tangents from the same point. Do we have that in this diagram? Yes, we do. This is the tangent PQ. And another tangent PT. What is this saying to me? It says this tangent PT is equals to PQ. If these two are the same, what type of an angle is this one? QPT. It's an isosceles triangle. Now, if this is an isosceles triangle and these two are the same, it simply means that these two angles will be the same. If that is Y, this will also be Y. Remember, if these two are the same, and I add this plus this plus this, what do I get? 180 degrees. The sum of interior angles of a triangle. I already have 80. To get 180, what am I short of? I'm short of 100. And those two will be the same. So this will be 50, this will be 50. So this is how we'll go about finding the value of y, that it is 50, by realizing that we've got two tangents from the same point that will make these two isosceles triangles, these two sides equal. It makes the triangle isosceles, and the angles opposite equal sides are the same. If this is y, that will be y. So this will be the same. So it's 50, 50 plus 80, it will give me 180, the sum of interior angles of a triangle. So that's how I will go about finding the value of y. That's how we'll go about finding the value of y. In this case, I've used tan radius theorem. Okay, in fact, they want us to find w first. Let's look at it. This is going here, and this is a tangent. So this value here will be 90 degrees. All right, that's fine. So I've already shown you how to find y. Let's look at x now. Where is x? X is here. We already know y. I mean w, which is 90, 50, x, 1, 2, 3, because this is a triangle. When we add these three, I must be able to get 180 degrees. We've got already the first 90. Let's find the second 90 from these two. So if this is 50, that will be 40 degrees. I've taken it from the sum of interior angles of a triangle. The sum of interior angles of a triangle. That's how we go about finding w. I think I've already spoken about y, that these are the two tangents which are the same. Then I use the sum of interior angles of a triangle to find the value of y to be 50. Angle z. I don't have to stress about z, I stress about theorems. Look at y. Look at the position of y. Where is y? This is a tangent, this is a chord. Y is between a tangent and a chord. Now, an angle between a tangent and a chord is equal to the angle subtended by that chord in the alternate segment. So if this is 50, as we are told here, so this angle here, it's between a tangent and a chord. I'll go with my chord to the circumference. So this angle here is the same as this angle, tan chord theorem. So if y is 50, therefore z will also be equal to 50 degrees. Right. Tan chord theorem, or angles in the alternate segment. Another problem, PQ and PT are tangents. These two are tangents, and they must be equal. So I know that this one is equal to this one, and there's no triangle, right? To a circle with a center O, center theorem. This angle is twice that angle. This angle 98 is 2 times that one. So y, if I'm looking for y, I've got to divide 98 by 2 to find angle y. Let's look at the question. Question number 1. Find angle W. Angle W. Where is W? W is here. You don't have to think of W, think of the theorems. What is the name of this line? This line is called the radius. What is the name of this line? This line is called the tangent. What do I know about the theorem that deals with a radius and a tangent? Whenever a tangent meets a radius, 90 degrees is formed. Therefore, angle W is equal to 90 degrees tan radius theorem. Let's look at x. Where is x? Let me go look at x. What do I see around this x? This is the line. What is this line called? OQ is called the radius, and this line is called what? A tangent. Whenever a tangent meets a radius, what do we know? 90 degrees is formed. Therefore, this value of x here will also be equal to 90 degrees tan radius theorem. Let's look at y now. Your eyes are the most powerful tool in your mathematics. Where is y? You design the circumference. Do I have the angle at the center? Yes, I do have the angle at the center. This angle at the center will always 2 times bigger than the angle at the circumference. Therefore, y will be half of 98, which in this particular case will be 45. I've used the angle at the center, or the center theorem. Let me look for z now. We know that from our grade 8, grade 9, if I add this angle plus this angle plus this angle plus z, I will get 360, not 180 now. The sum of interior angles on every four-sided figure is 360. So we've got this as 90, we've got this as 90, so it's 90 plus 90 plus 98 plus z will give me 360. Therefore, z will be equals to 82. I've used the sum of the interior angles in a quadrilateral. We've used that, the sum of interior angles in a quadrilateral. Alternate segment theorem, which is the tan chord theorem. The angle between a tangent and a chord through the point of contact is equal to the angle subtended by that chord in the alternate segment. We abbreviate all this by tan chord theorem. This is a chord, this is a tangent, the angle between a tangent and a chord. Let's have the angle between a chord and a tangent. Let's call it x. Now, to find the angle that will be equals to this x, I've got to take this chord and form an angle at the circumference. That is the angle. So this angle, which is formed by this chord at the circumference, is equal to the angle between a tangent and a chord. So if this is x, this angle that will be formed there will also be equal to x. I don't have to be stereotyped. Even if I'm coming from this side, I must be able to see that this y is between a chord and a tangent. I go with this chord to find the angle at the circumference, which will be this one. So this angle there will be the same as this one, tan chord theorem. So that becomes crucial. Let's do a few examples. Find the missing angles below, give reasons for each. I'm given 45, I'm given 60, I'm looking for all the other ones. The first one that I'm looking for is the value of x. There is x. I take it back here. Look at this one. This is a tangent. This is a chord. I go with the chord to find the angle which will be equal to 45. In this particular case, angle 45, angle x will be equal to 45 tan chord theorem. Let's look at what? Z. The next one is y. We're looking for y. Y is between a tangent and a chord. Ngizohamba ngale chord and find the angle that is formed by this chord, which is 60 degrees. Therefore, y is 60 degrees. Remember this scenario? These two are the same. These two are the same. It's exactly the same thing. Therefore, y is equals to 60 degrees. So that becomes very important. Right, even when we are looking for angle y, it will be equal to 60 degrees, subtended by this chord. It forms it at the circumference. Therefore, angle y will be equal to 60 degrees. Let's look for angle z now. This is where z is. There are too many ways. This is 60, this is 45. So this is a straight line. The sum of angles in a straight line are supplementary. So 45 plus 60 plus z will be equal to 180. That's one option. Option number two, it can, but remember this is also 45. 45 plus 60 plus z will be 180 if I'm using the sum of interior angles of a triangle. So I'm spoiled with choice. It's either I use the sum of interior angles of a triangle, which is 180, or I use the straight line, which is also 180, to find the angle z, which will then be equal to 75 degrees, the sum of interior angles of a triangle. So it's z plus 60 plus 45, which we find from here, plus 45 will be equal to 180. And that way we'll be able to find our angle z. Mixed questions. PTR is a tangent line to the cyclic T. PTR. Once they say PTR is a tangent, I think of three theorems that deals with the tangent. All right? Do I have two tangents from the same point here? No, I don't have. Do I have tan radius? This is a radius. This is tangent. Oh, I do have it. So this whole angle here will be 90. If this is 65, what should I add to get 90? This will give me the size of this angle. In that, let me see what they are looking for first. And find angle SUT. SUT. We're looking for that angle there. And we're given this one. What forms that angle SUT? It is formed by this chord, ST. ST subtends angle U, the one that I'm looking for. And this one is a tangent, and this one is a chord. The angle between a tangent and a chord is equal to the angle in the alternate segment. So SUT will be equal to 65 degrees, the tan chord theorem, or alternate segment. That's one. So we do have this angle as 65. What is the next question? SOT. SOT. Where is SOT? SOT. It is at the center. Do we have the angle at the circumference? Yes, we have it as 65. Which one is bigger? The one at the circumference or the one at the center? The one at the center is 2 times bigger than that one. If we have this one as 65, this one will be 65 times 2, which will give us 130 degrees. Because this one is the angle at the center, which is twice the angle at the circumference. So we do have this one, we do have this one. We're now looking for OTS. OTS, this small one. Remember that angle from there to here is a radius, and it meets a tangent. Therefore, this whole angle here will be 90 degrees. 65 plus what must give me 90? It is 65 plus 25. So this angle here will be 25. I've used the tan radius theorem. This is the radius, this is the tangent. Therefore, this whole angle will be 90 degrees. 90 degrees. So this one is actually 25. If this one is 25, what will this one be? Remember, this is an isosceles triangle. OS is equals to OT, radi, on the same circle. This one circle will have the same radius. From here to here is the same, from here to here is the same, from here to there. Radius is the same. So if these two are the same, therefore these two will be the same. So if I'm looking for OST, this angle, it is the same as OTS, which we've just found above to be 25. We've used the isosceles triangle. So that's how easy Euclidean geometry is. We are not afraid of such complicated problems. We are armed with our theorems and the statement. PR and P2 are tangents. There are only 3 theorems that deal with the tangent. These are the 2 tangents from the same point. I see them. Therefore, this side is the same as this side. UP is the same as PR from the 2 tangents theorem. If this is X, that will be X. I know that much. But let's find the questions first. Question number 1, find angle W. This is where W is. Okay, I can see a cyclic quad. Do you see a cyclic quad? Do you see a cyclic quad? You then go down, come this side, come this side. That's a cyclic quad. Yes, I do have this angle, which is 110, and this angle. All of that angle, W plus 48 plus 110, must give me 180. Right? W plus 48 plus 110 is equals to 180, opposite angles of a cyclic quad. If this is 110, whole of this must be 70. So 48 plus W must give me 70, therefore W will be equals to 22. Because 22 plus this is 70, 70 plus 110, it's 180. So the sum of opposite angles of a cyclic quad are supplementary. Just apply your theorems. Let's look at X now. We do have this as what? As what was our W? W is 22. We do have 22. What is this line called? It's called a radius. What is this line called? It's called a tangent. Whenever a radius meets a tangent, 90 degrees will be formed. We already have 22. So it's 22 plus what? That will give us 90. So X will be 68. 22 and 68 will give us 90 degrees, tan radius theorem. Let's look at this next question. I think they should be asking about Y. Yes, they're asking about Y. We do have our X as 68. Remember, we've got 2 tangents from the same point, which is point P. If this is equal to this, so X will also be the same as X there. So if this is 68, we've got 68 plus Y will give us 180. Those 3 must give us 180. So 68 plus 68 plus Y will give us 180. So the value of Y in this particular case will be 44 because we've got an isosceles triangle. Right, we've got Y. Now we're looking for Z. Okay, look here. Look at this angle here. This is angle X. What is angle X? It is 68 degrees. Where is angle X? It is between a tangent and a chord. I go with this chord to the circumference. It will take me to angle Z. So angle X is the same as angle Z, tan chord theorem. So angle Z will also be the same as angle X, which is 68 degrees, tan chord theorem. So whatever I'm given, I know that I've got to use theorems to solve. These are some of the important people that studied geometry. Thomas Hobbes, Abraham Lincoln, US President, they all studied Euclidean geometry. Even Albert Einstein studied Euclidean geometry. Yeah, I want us to go straight to exam problems now. We were going to do the proofs of these theorems, but we'll do it some other time. I want us to go straight to problems. Thank you.